So, using 4 vector property of energy momentum, we derived last time that E square minus P square C square should be invariant under Lorentz transformation, because the vector is E by C, that is the 0th component, and then Px, Py and Pz, this is the 4 vector, and magnitude of this vector squared is minus of this quantity and then plus this square plus this square plus this square, which is P square. So, this is like a magnitude of the vector square, and hence you go for transformation, change to different frame, you are essentially multiplying this quantity with that transformation matrix and you get new components. So, energy is different, Px, Py, Pz are different in the new frame, but then the magnitude square of the vector, that does not depend on the frame, and hence this is constant, and therefore E square minus P square C square is invariant. That is what we discussed. Now, we can check this for a single particle. A single particle means inner structure does not change. If inner structure does not change, if there are subparticles, if there are parts, and that parts, the movement of parts or interaction of those parts, if that does not change, we can treat it as a single particle. So, for a single particle, you know that E is total energy, this E is total energy, this is m naught c square times gamma, and this whole quantity is called the relativistic mass m, and then you write E is equal to mc square, and P is given by, let us take going in x direction. So, P will be m naught times V and then gamma, that is square root 1 minus V square by C square. If you take vector, it is this, that is P. So, what is E square minus P square C square? For this particular case, a single particle, you can calculate from here. So, E square and minus magnitude of linear momentum square and into C square is equal to square of this. So, m naught square and C power 4 divided by 1 minus V square by C square, and then minus P square and C square. So, square this, magnitude square this and multiplied by C square. So, it is m naught square V square C square. So, m naught square V square and then C square and divided by 1 minus V square by C square. So, you have 1 minus V square by C square here, and then m naught square C square you can take common. So, you will get C square from here and minus V square by from here, and this you can write as C square minus V square by C square, and this is m naught square C square, and then you have C square minus V square, cancel this, bring it up, and this is m naught square C 4. All right. So, this is invariant anyway, because when you change frame, you go from one frame to the other frame, and this particle, the same particle you are seeing from this frame and that frame. So, that inner structure is not changing. So, only the speed is changing, velocity is changing, correspondingly total energy is changing, momentum is changing, but this rest mass m naught remains the same, and therefore m naught square C 4 remains the same, and therefore E square minus P square C square remains the same. So, for a single particle you have another good relation, E square minus P square C square is equal to m naught square C 4. Useful, very useful equation. E you can write as square root of P square C square plus m naught square C4. For a single particle, remember, for a single particle. If you have a combination of two particles, two different particles, and then you write total energy E1 plus E2, then you write total momentum P1 plus P2, you still have a 4 vector. The total energy of two particle system, the total linear momentum of two particle system x component, the total linear momentum of two particles y component, the total linear momentum of two particles z component. If you write these, it is still a 4 vector, and again minus of this square plus this square plus this square plus this square will remain invariant. But then it will not be something like total rest mass of the two particles m01 plus m02 square c to the power 4. That is not guaranteed, that is not the case. But whatever it is, it will remain invariant. Now, a single particle, this equation itself is a very important one, and one use is, if you want to decide whether relativistic dynamics is needed or Newtonian non-relativistic dynamics will be okay. So, if you want to have that kind of assessment, how much should be the velocity, how much should be the energy, how much should be the kinetic energy, so that relativistic mechanics is absolutely necessary, otherwise the errors are beyond acceptable limits. So, this equation can help, Your E is the total energy, which is rest mass energy plus kinetic energy, remember, and then you have this equation. Now, if this total energy is much larger than m naught c square, rest mass energy, or the kinetic energy is much larger than the rest mass energy, if k is much larger than m naught c square, and if that happens anyway, E will be much larger than m naught c square, that means the relativistic correction is very much needed, you have to go for it. Okay. So, the comparison is with this rest mass energy, and linear momentum from this side also is the same thing, P square C square, or Pc should be much greater than m naught c square. Any of these criteria, whatever is available to you on kinetic energy, total energy or linear momentum, you compare with this rest mass energy. Pc can be compared with rest mass energy, total energy can be compared, kinetic energy can be compared, and then yes. So, for example, suppose you have an electron, right, suppose you have an electron. Now, for an electron, the rest mass energy is 511 keV, several times I have mentioned that. Now, if this electron is, suppose these are two plates, positive and negative capacitor plates, and then this electron is moving with this electric field, and when the potential difference is, let us say, 100 volts of potential difference. So, when it moves okay, let me write it this way. So, the field is in this direction, so force is this direction. So, from here when it reaches here, the kinetic energy is increased by 100 electron volts, right. If it is released from rest from this plate and reaches here, then the potential energy increases by 100 electron volts, the kinetic energy potential energy decreases, kinetic energy increases. So, when it reaches here, the kinetic energy become 100 eV. Should I apply relativity? Unless I am doing very sophisticated measurements with a lot of accuracy, 511 kilo electron volt. So, this is 511,000 eV, and this is 100 eV. So, this is much smaller than the rest mass energy, unless I am doing very sophisticated experiments. okay, it is 1 in 5000. So I will say that okay, Newton is okay, F is equal to ma and half mv square and all that acceleration, and v is equal to u plus at, and all those things will work very well here, it is okay for me. But then if you are accelerating an electron in an accelerator, linear accelerator, if you are accelerating an electron with, let us say, 1 megavolt of potential difference, which is a very small energy if I am talking in terms of the accelerator laboratories. 1 mega electron volt energy in any accelerator laboratory is a very small energy range. So the kinetic energy of the particle of this electron is 1 MeV as it goes from this end to that end, electron. If kinetic energy is 1 MeV and rest mass energy is half MeV, 511 keV, Newton's laws F equal to ma will not work. You have to go for relativistic equations. But if you have a proton which goes through the same accelerator and the proton kinetic energy becomes 1 MeV. So instead of electron, if you have a proton going through that same 1 MV potential difference, and 1 MeV becomes the kinetic energy. You can still use Newton's laws because the proton rest mass energy is 938 MeV. So if it is 1 MeV in front of 938 MeV, if you are not doing with sensitive instruments, etc., it is acceptable perhaps, but with the same setup, 1 MeV electron, it is not acceptable. So this equation can be used for these kind of considerations also. Let me make some space. Now we had been talking of S and S prime, and these notations are for a very specific situation. From the very beginning I have said that whenever I will use S prime, I will have this convention that S prime moves in positive x direction with respect to S, then x prime axis and x axis coincide all the time, then y prime axis is parallel to y axis all the time, and of course then z axis will be parallel to z axis all the time. And on top of all these things, we also have that time t equal to 0 and t prime equal to 0, that also very specifically we defined for this, that origins, when origins cross this event, the two origins are at the same place. S prime is coming from one side and moving with respect to S. So at some instant the y axis coincides with y prime axis, z axis coincides with z prime axis, and the origin O prime coincides with origin O, just one instant. So that that event we say that will be read as t equal to 0 in S prime and t prime equal to 0 in S prime. What if these conditions are not met and I have to work from a frame which is moving with respect to S, but perhaps not in x direction? perhaps the orientation of the axis are different. X prime axis is not coinciding with x axis and it is at some angle. So, the Lorentz transformations equations that we had written will not have that form, right. The Lorentz transformation equations were x prime equal to x minus vt. These were our equations, y prime is equal to y, z prime is equal to z, and t prime is equal to t minus x v by c square, square root 1 minus v square by z square. These are the equations we have practiced from the very beginning, and we have crammed perhaps by this time. But then these equations, this will not be the Lorentz transformation if these conditions are not met. Lorentz transformation will always be there. Relativistic, our world is relativistic, no one can change that. But these forms will be more complicated. But we can say some things about our components of a 4 vector, even if axis system are different, even if S prime is not described through this prescription. If we have our E by C, Px, Py, Pz, prime, 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 you will have a transformation matrix. If these conditions are fine, then I know what is the transformation matrix. Just coming from here, I know what the Lorentz transformations are, equations are, and then I can write this in a tabular form, and you have gamma minus beta gamma 0 0, that matrix. If it is not, this matrix will be different, these equations will be different, and if these equations are different, then this matrix will be different, and then you will have this E by C, Px, Py, Pz. So now I don't know how to get E prime from these quantities, how to get this Px prime from these quantities. Py prime will no more be Py, it will have some combination. So depending on what kind of S prime I have chosen, this matrix will be different and the relations will be different. But one thing I can be very sure of, if I consider this quantity E prime by C square with a negative sign plus Px prime square plus Py prime square and plus Pz prime square, and here I construct this quantity minus of E by C square and plus Px square and Py square and Pz square. They are going to be the same, whatever this matrix is. After all, it is only changing the frame. So when I am changing the frame, I am not changing the magnitude of a vector. In 3-dimensional geometry, when we have x, y, z axis and there is a vector, the length of the vector will not change if I reorient the frame. Similarly, here in this, if I am changing from one inertial frame to other inertial frame in whatever fashion, that length of the vector, that will not change, and this is, it represents that length of the vector, magnitude of the vector, square of it. So this will be equal to this. This I can still say. So E prime square minus P prime square C square, that will still be E square minus P square C square, and that is valid for all 4 vectors, all kinds of 4 vectors, position 4 vector or displacement 4 vector, any vector, or velocity 4 vector, any 4 vector you take, this will always be there. So not necessarily it is coming from this kind of equations. I had shown few minutes ago that if I use these Lorentz transformations and get the expression for Px, Py, Pz and E and all those things, energy, total energy, I can work out what is this, and it came out to be a constant independent of the frame. But not necessarily, even if it is, I am not going through these equations, even if this prescription is not valid, this is true. And it is property of 4 vector. Therefore, same thing I can say for minus c square t square plus x square plus y square plus z square. Same thing I can say for this. No matter how you are going from one inertial frame to other inertial frame, whether the axis of other inertial frame you have chosen which are parallel to the original axis of the first frame or not, whether the second frame is moving in x direction or not, whatever, this quantity is not going to change. Although x prime cannot be obtained from this equation, t prime cannot be obtained from this t prime cannot be obtained from this equation, y prime and z prime, they cannot be so simply obtained from these equations, but then this equation will still remain the same. Okay, so those are the kind of properties of 4 vectors which we can employ and get some relations even if our frames are different. Now, the last thing I want to say in this lecture is the conservation of energy momentum. Say this positions you have seen from position vector, position 4 vector, the space coordinates and time coordinates, they get mixed up. And that mixing up, we say that okay, there is one entity space hyphen time, and space and time are like components of space time. When you choose a frame, you have fixed up, okay, this is space and this is time. Similarly here, energy and momentum are mixed up. So in one particular frame, yes, you have a separate existence of energy and separate existence of linear momentum. But when you change to some other frame, this energy is not related solely to this energy, this linear momentum is not related solely to this linear momentum, just like this position x is not related solely to this position x, or this time here is not related to time here. So time and space are mixed up. Similarly, energy and momentum are mixed up. They are component of say one quantity which you can call energy hyphen momentum. When you fix a frame, yes, you have a separate formula, separate equation, separate interpretation of energy and separate interpretation of momentum. But when you change frame, they get mixed up. So it is this, and the linear momentum conservation principle and energy conservation principle are in fact combined to say that this energy momentum remains constant if there are no forces on the system. So if there are no forces, on the system, this energy momentum remains constant. Distinguish between invariant and constant. When I say that this is invariant, I have in mind going from one frame to other frame, this quantity does not change. When I am saying this is constant, I have in mind that I am using the same frame. Time passes. The system may change, may undergo changes. Its energy and its momentum, that has to be seen. If no forces are there, no external forces are there on the system, then this energy momentum remains constant. I am using the same frame. So when I am changing the frame and finding the value of some quantity in this frame, that frame, and it is same, then we say it is invariant. And here it is as a function of time, some interaction is taking place within the system, not from external forces. Because of that, things are changing, configurations are changing, and we see that in all those situations this energy momentum remains constant. And remains constant means all the four components remain constant. In usual Newtonian mechanics, when I say linear momentum is conserved, I mean that px is separately conserved. In x direction, the x component of the momentum remains constant as a function of time. Y component py remains constant as a function of time. Pz remains constant as a function of time, and also this E remains constant in time. All the four components remain constant in time. Okay. So this means all the four components. So energy and momentum are now brought under the same umbrella. All the four components remain constant or conserved. So that is the principle of conservation of energy momentum.